Everyone, welcome to today's delayed session, so thanks for being patient. My name is Chris Bantine, and I'm Chief Technologist at the West Coast for Red Hat, and I've been with Red Hat for quite a while, and I'm going to talk about today enabling microservices and databases that are containerized with Kubernetes. Feel free to ask any questions as we go, or at the end I'll be around as well. I like to talk about kind of the business drivers for technology before we dive into the tech. So first off, start with a quote from Andy Grove, "Only the paranoid survive." Has anybody heard this quote before? Right? This isn't about security, but it's about strategic inflection points. Right? Most companies have a point in time when there's massive amounts of disruption going on around it. Maybe it's new competitors, new technology that's having a huge impact in terms of the company's go-forward strategy. And they have to reassess. Do they stay the course and potentially become irrelevant, or pivot, change direction, and potentially thrive? Certainly Intel has had a couple of these in their time when they switched from DRAM to the CPU. There's a lot of internal conflict on whether they stay in the DRAM market or CPU market. And certainly again in the Pentium bug, do they respond by replacing the CPUs right away or not? And there was this internal conflict because Intel was traditionally an OEM provider. But what really changed was this Intel Inside campaign. And they started marketing to consumers. And when there was a Pentium bug, there was this expectation from consumers that they would react in the way a consumer company would by issuing a refund or a replacement when there's an issue. But internally, they were stuck acting like an OEM that wouldn't replace it. And so this conflict caused them some delay, but they had learned from their experience from DRAM to CPU. In a matter of weeks, they quickly changed course and turned direction in terms of replacing the CPUs for the Pentium bug. So really having your pulse on the market and being able to respond quickly was key to thriving with this inflection point. And so many companies out there are having a lot of pressure on them because of the disruptors are disrupting the incumbents, mainly because of technology innovation driven by software and automation. And legacy companies are having a hard time of shifting from a focus on execution to one on innovation. Right? Transportation industry is certainly a key example of this. You have Ford, great at distributing cars around the globe, but short on innovation. When you compare it to someone like Tesla, it's really embraced software in a more dynamic and policy driven. Right? It's allowing them to rapidly innovate and stay ahead of the incumbents. And so automation is certainly a key part of that transition. This is the Tesla automobile factory. Software is a key enabler for them right now to ramp up their Model 3 production rate. Robotics are being driven by software and automation to get to those weekly numbers. And software is a huge part of this vehicle once it leaves the dealer lot. For the first time, a car actually gets better 3, 6, 9 months down the road. They're able to deliver software updates over the wire, improving the 0 to 60 time, battery efficiency, or a security update for the autonomous software in the vehicle, whether it's a new improvement or a security fix. And fundamentally differentiating them from the competition and fundamentally evolving their business model from a one-time sale to a reoccurring subscription potentially with new and added features. And so we've seen this before. Under the covers, the software factory, in this case the fab at Intel, has enabled them to become the differentiator in their business over the years. It hasn't been their architecture, right? It's been the fab. And likewise in the modern era, we have Amazon, Google, Facebook. Their differentiator is software-based with this large software factory that can quickly produce new software in a very automated way, in a very frequent way. And if you look under the covers, some of the key differentiators for these disruptors is the ability to shorten that feedback loop. Right? Think about that Intel case. Right? They were able to respond a lot quicker that second time around with the Pinion bug versus the DRAM to CPU shift, which took years, because they had their pulse on the market. Right? They had real-time data on the market back then. Likewise, today, Uber has real-time pulse on their market, and they're able to dynamically shift and change their pricing based on demand, supply and demand of riders and drivers. They also have fostered a culture of experimentation. They're enabling their developers to rapidly try out things and experiment. And they're able to speed up the delivery part. Right? They've empowered their organization from a cultural perspective, breaking down these silos, and empower the individual developer and product manager. And when they are able to produce that new thing, they're able to get it out into production quickly. Right? They have an automation assembly line or pipeline that allows them to move from dev test to production in a matter of minutes. But the typical enterprise can't do that. Right? It takes them 6 to 9 months to deliver new components because they have walled off processes, tools, and technologies that make it very difficult for these cross-functional groups, dev, test, security, database, production operators from collaborating. And so they've siloed it off into separate environments, separate organizations. And so that's why you're seeing the evolution of IT, right? To a DevOps microservice base in containers on this hybrid cloud infrastructure that scales up and scales down. And some of the key fundamentals of this shift is the cultural shift, right? From an open source perspective, it's really reflective of where things are going. Open platform, open culture that brings folks together and allows you to innovate rapidly, right? No one is smarter than everyone. And that's the power of open source. They're able to leverage a community of people that quickly innovate. And then process automation, right? Making it agile, the ability to deliver quickly in a highly scalable and predictable manner, and managing your infrastructure as code so it's reproducible, configurable, and consistent, and automatable. And then, of course, this transition is being fueled by open source technologies, both at the infrastructure and the operational and development perspective. And so containers are a huge part of this shift because they enable you to package your application once in development and then deploy anywhere in a lightweight container that's portable across any environment, physical, virtual, private, public cloud. Right? You've totally abstracted the underlying infrastructure from the developer in the application. And this enables rapid production of new technology and the delivery of it. And this is made possible from a technical perspective. Similar to the Java world, you have the JE spec. We have a standardized runtime and a standardized packaging format. Well, in the container world, there's the Open Container Initiative, which is standardized the image format, the distribution spec, so I can share that image across different providers, different environments, and a standardized runtime. It's not just for Java code, it could be any application, development language, C, Python, Perl, etc. You can package that application and you know that it's going to run because there's been standardization and multiple vendors can come out with their own implementation of that standard. But containers are great on the developer laptop, but what about managing containers at scale? There's a lot of capabilities you need in a real enterprise when it comes to deploying hundreds or thousands, tens of thousands of containers across one availability zone or multiple. And so things like scheduling. You want to be able to schedule your container so that you effectively and efficiently are able to meet the requirements and efficiently consume those resources and lower your costs. Also, to manage the life cycle of that container, of packaging it, deploying it, retiring it, scaling up, scaling down, etc. And if there is an issue, I want to automate the detection of that and keep my microservice or application running as is. And then discovering. How do I discover these services in the cluster? How do I know that they're available? How do I monitor them and get observability into how my system is performing? Scaling up and down, so I don't have to open a network engineering ticket, which may take hours or days to fulfill, to scale up my app and anticipate when there's new load or increased load. And then also persistence. I don't want to just develop container native applications and manage them. I want to bring all the capabilities, the benefits in a container environment to my legacy existing applications. I don't want to invest taking that and re-architecting it. And so persistence is a key part of that. And then aggregation. How do I aggregate multiple microservices, manage them at scale without having to worry about are they distributed for high availability? And certainly security. How do I update them in a very efficient manner? So we're going to talk about that and much more. About Kubernetes, I really view it as this automated software factory that we were talking about earlier, that the internet companies are using as a differentiator for their business. But this does it in a very standardized way, rather than a do-it-yourself, not invented here type of approach that is standardized and can be a cloud-agnostic solution for your application set. I can run it across bare metal, virtual, private, or public cloud. Think about that. Kubernetes is empowering me to eliminate that lock-in. It's really the Linux of the cloud era. That same benefit. You see the cloud providers more like a Unix provider with their proprietary APIs and offerings, and then Kubernetes can be layered on top of those, can leverage those, but bring abstraction so I'm not tied to a single provider. If my business needs data residency in a remote geography where I don't have a local data center and that data needs to be local, well, I can set up a provider or select a provider in that geography and deploy Kubernetes. I don't have to rewrite my application to that provider's specific services or change the way I manage, both from an operational and from a security perspective. And so I'm going to go into a deep dive in terms of automation, some of the fundamentals of Kubernetes, if you're not familiar with what it has to offer. Images, builds around containers. How do you integrate it with a CICD process, as well as security? So first off, some of the basics around Kubernetes. One is orchestration. This is one of the key fundamental things that it automates. Today, maybe your developers or you are writing scripts to move applications into production, to make sure that they're highly available, to automate the setup of the network, the storage, scheduling of the compute. Well, Kubernetes standardizes that so your developers and operations don't have to do that. And I can define an application. It's declarative, so you define the state, and then Kubernetes ensures that your application is deployed in that state at all times. And it tries to recover if there are any issues and maintain that state. So in this example, I have an application that consists of two microservices. One is a web front end, and then the second is the application backend. Well, I want the web front end to have two instances and the application to have a single. And so I've defined that, and I've defined the container image that those instances are, HTTPD and my app 1.0. Well, Kubernetes, with its controller manager, will actually go ahead and schedule that. And in a Kubernetes cluster, you have what's called a nodes. That's just a physical server or container instance on Amazon, for example. And the Kubernetes scheduler will go ahead and place those containers in what's called a pod. A pod is just one or more containers running on a node. In this case, you have two web servers placed in a single app server across that. And so it intelligently placed the web server on two different nodes, so you had some redundant high availability there. And it pulled those images from the image registry. Could be outside of the cluster, or it could be actually running in the cluster. And then it front-ended each of the pods with a service. And the service will route the traffic to the pods. And the way it discovers the pods is that there's some labels, in this case a role of web and a role of app, and then the service are defined based on that label. So it will automatically add anything with that matching label. And so here for the web service, it actually will route traffic across the two different web pods in my cluster. And then secondly, it set one up for the application. And then it also, for the web traffic, set up the ingress so it routes traffic from the outside to the internal network here. The second thing it does is it does a health check, right? So now that I have it running, it's constantly monitoring it to see if it's receiving a request and responding. And if it doesn't, it'll flag that as being non-responsive via the health check. And then the scheduler will automatically schedule a new instance to replace that failed one. Right? And once it's up and running with the readiness probe, it'll update the service and replace the existing failed one with the new one based on the label here. So now I retain that state, so it's declarative, meaning it's always going to be a 2-1 configuration. Now, another key feature of Kubernetes is auto-scaling, right? So I can dynamically scale up. In fact, you can scale down as well. But in terms of this example, here I'm running my 2-in-1 configuration, and I'm monitoring the resource utilization. And I've set a threshold of 80%, and it exceeded that, or equaled it. And so what it did is it automatically deployed a additional application server. So it redefined it to replicas of 2 and found an available node to run that. So now I'm going to run a 2-in-2 because of the increased load on my application server, and you can see the CPU went down. So orchestration, health checks, and auto-scale. Some of the key basics in automation, something that you're probably scripting or manually doing today that it accomplishes in a very standardized way. That's cloud agnostic. Second thing is container images. Talk about containers. So the basic for a container image is that you have, similar to a make file, but a build file, of a recipe of how to build that container image. You can specify a base image that you want to build upon, and as well as additional components they may want to bring in, maybe RPMs. And then you produce a container image, and you store that image in a registry, which can be distributed, pulled from across different environments. So build it once in development, and now make it available as is in test and production. And then I run it and deploy it on my cluster, and it instantiates from the image a container instance. So an image becomes an instance. And I can run that on a physical virtual cloud because of the standardization on the runtime. Now the container image itself, you know, you're coming from a world, if you're in Java, where you create and deliver a jar file to test into production. And the tests and the operations provide the rest. Well, in a container world, you actually deliver a container image from development to test and production. Right? So no longer is it just my jar. I now have that jar or microservice, and it pulls in any language runtime dependencies as well as any OS dependencies. So I have all the dependencies I need inside that image. What does this mean? This means I now can have multiple versions on the same host. I don't have to worry about a dependency not being there, or everyone having to have that exact same version of a dependency as well. Right? So it gives me a lot of flexibility in terms of deployment and multi-tenancy, and therefore greater efficiency, and each team can choose what components they need for their microservice or application. Also, a principle around containers is to treat them as immutable. So how do you do that in a Kubernetes cluster world? Well, there's some ways to, some concepts that take advantage of keeping your images immutable. And that means the image doesn't change, right? Do not store configuration information, do not store data in the actual container image of your application. And so in order to accomplish that, Kubernetes has what's called a config map and a secret. So if you have some sort of configuration, maybe it's an IP address, username, something like that, you would store, for example, the IP address in a key value pair called a config map. And if I had a password that needs encrypted, similar, there's called a secret, which encrypts it. It stores it on the Kubernetes cluster in a etcd key value data store. Now, if I have data that that application needs to remain persistent, I can store that by accessing a remote data service, a database, for example, JDBC connection, or I could mount automatically some persistent volumes into my container instance and store it there. Right? That could be network storage, NFS, block, Ceph, etc. So those are two concepts to keep your config and data outside of the image. Now, to show you a config map, a typical example would be maybe a configuration file for the application. Maybe it's JBoss, and you have an XML file. Well, what you can do is you can version control that XML file for your JBoss configuration in Git, and then you can import it as a Kubernetes config map as a key value pair. So it would import the entire file contents as the value for that config map. And then when I go ahead and launch that instance of that image, it will go ahead and create the instance from the image file, and then it will actually either set that config map as an environment variable or save it as an actual file within that instance. Right? And just a note, the environment variable requires the pod to restart to refresh it, whereas files get refreshed automatically. So some best practices as you are building out build files. Here's an example on the left of a well-written one. Is first off, treat the build file as a blueprint, right? Just like your makefile, version control it. Don't log into an instance, make changes and save because you don't have that saved in the build file. Be explicit with the versioning. Don't just say latest. Make sure you're explicit there, registry.redhat.com, in terms of what registry you're pulling from. And then all container images by default will run as root. We don't run as root in production. So make sure you're specifying a user in that file. And then just be aware that each time you put a run, it creates a new layer. And then image container build. So how do I go out building my own custom ones? The basic flow is you develop your source code, and then you create your RPMs as you traditionally would, but then you create a container image. You save that in your registry, either private or public, and then you pull from that registry and you deploy out to your Kubernetes cluster, either in dev, test, or production. Now, one of the things we saw there with a container image, it doesn't just have the jar file, it has the application dependencies and it has OS dependencies too. So who is watching out for new releases to address bugs and security fixes? Is that the developer's responsibility now? No. You can separate responsibilities with the developer just owning the code layer, but building on top of other layers. So the middleware team can build an image that has, for example, the JBoss middleware built on top of RHEL 7. Does the middleware team have to maintain updates for RHEL 7? No. The operations team can maintain that base image of RHEL 7. Right? And so think of these as building blocks and each team owns their own individual block, and then you can put them together however you'd like. Another key thing that you can then do is once you have that image out in production, or a new version comes out, so let's say the OS team updated Rel 7 with a security fix, you can set up an automation to check that registry if a new version is available, to then trigger a rebuild of anybody that depends on it. Right? So I, as a developer, don't have to be watching out for new Rel 7 images. It's just automatically notifying and then creating a trigger to then rebuild my application because it depends on that particular layer that has been updated. Right? And so if you have a CICD pipeline with Kubernetes, typically it would look like this. You running on some sort of infrastructure, one or more of these, and then I can have all these environments logically defined on top of that same infrastructure. So dev, test, and production can live on the same physical hardware. It's just logically separated, and we'll explain how in a minute. But from a developer perspective, I'm checking in my source code, I'm checking in my build file, and then I go to the build phase. But what I leverage in the Kubernetes pipeline is I would typically want to use a build image. A build image is a container image with all the build tools necessary for my application or service. And it knows how to build my solution. It's also version control. And then it will output my application and then bundle it in with whatever application OS dependencies minus all the build tools and intermediary files. Right? So it's lightweight and just has what's necessary. And then I store it in that image registry. I can then deploy it to development, test, and then production. Right? And so a best practice for that build process, try to achieve a reproducible build. Like, what does that mean? That means if I build it the second or third time, I get the same result as the first time. And how do I go about trying to get there? You know, it may not be 100%, but you're definitely getting close to it. And the way you do that is you have your source code, of course, version control, but I also version control my build image. This is a container image, as I mentioned, which in this case has the Java build environment. And then I version that, and then I then take my source code with my build image and I produce a container image, which is also version control. So 6 months down the road, I want to go back and reproduce version 3.1. I now know that it was version 3.1 of the source code and it was the version 101 of the build environment, right? So I can go back. And another key reason to be doing this is security vulnerabilities and attacks are not all about changing source code. They're also about hacking into your build environment and injecting change, unwanted change in there as well. Maybe they swap out the compiler and automatically you're producing a binary that has some vulnerabilities in it that are not going to be discovered by doing source code scanning. All right, container image security. All right. So what's inside that container matters. We did a scan of the public Docker Hub repo, found 64% of the images had a medium or high vulnerability. So developers pulling down these public images, do you know what's in that image? Can you trust that image? Right? And so a best practice, and pretty much the first thing we see on the container journey, is the operations team setting up a private registry for the development teams. This provides a trusted, known source for your content and an audit trail of who's pushing and also accessing this content as well. Another best practice then is also to sign those images so you know where that image is coming from, the integrity of it, and you, in Kubernetes, you can actually prevent the image from becoming an instance upon initiation if it doesn't come from a trusted source. Another thing about security in a container is that what's inside matters. Here we have a Java or a C, Java, Node.js, Perl, PHP application, and on the second column, there's these are the components that got pulled in. So the JRE got pulled in, Bash, glibc, and the triangle indicates how many security notifications have been issued for that component. The JRE has 66, and it's much higher than that. This slide's a little old. And so what that tells me is not only do I need to be worried about is that a trusted source I'm getting my content, but I need a process on an ongoing basis to be scanning my images. And so one of the best practices is to insert a security phase into your CI pipeline. Right? So as you're building your application and then you build the container, run it through a security scan. There's a variety of tools out there from a variety of companies. One of them from the upstream community is called OpenScat. You know, there's content that's maintained for vulnerability information from an RPM perspective. There's also predefined compliance policies for you, so you can define a security policy. You can run this tool to see if there are any known vulnerabilities from an RPM basis, or if it doesn't conform with the security policy. And then you get a report and remediation. So it can create an Ansible script and rectify a policy or vulnerability issue. And so here's just an example of some of the security policies out of the box. You can modify them. You also get a report. When you run the scan, it tells you how it doesn't comply, that particular image, with your policy. Maybe it's the password length, etc. And if you click in there, you can actually drill down and get a script to apply to remediate that particular issue. Right? So security vulnerability scanning and security policy or compliance scanning. Now some registries also, if you have a registry service, either public or private, some of them will trigger a scan, either an internal or external tool every time you push a new image. So you can integrate that into your process as well. So we talked about the CI/CD pipeline with Kubernetes. You had dev, test, and production all on the same infrastructure. How was that accomplished? Well, network security, right? So network namespaces is built into Linux, which enables you to carve up your infrastructure into logical separated environments. So for example, I can have dev, test, and production all sitting on the same host, right, but just logically separated via network namespaces, as well as I can have 13 applications with 13 different networks all needing isolation from each other. And so that can be automatically configured and defined via Kubernetes, leveraging the underlying Linux. Also, from a network security perspective, I can define what's called network policy. Right? This is at the TCP/IP level, where I can define and restrict pod-to-pod interaction. Right? So if I want to create a whitelist, blacklist, I can define that and restrict communication from one pod to another to make it more granular. Next, I'm going to talk about deployment strategies. Over to what's next. Right? So, you know, this movement towards DevSecOps, integrating security. Well, a key part of that is being able to quickly respond and deploy updates to your environment. And so we're going to talk about some of the automation that Kubernetes brings to enable DevSecOps with automated deployment strategies. So if you look at a container pipeline, dev, QA, staging, production, you know, in the physical or virtual world, if there's a security vulnerability or need to up a patch, you typically go to production and you make that patch, right? In the old days, that's because, hey, the application is this monolithic app that has a lot of custom configurations manually built. It's just a lot easier to go do that. But in the container world, it becomes more of an assembly line where you don't actually patch production. You always go back to square one in development and produce a version N+1 to address that security or bug fix, right? And you push it through the entire process. That means every container image goes through that security scan phase as well before it gets into development, before it tests or production, depending on how you've configured it. And so when it comes to then pushing it out into production, you're not just doing that to a single host typically. It might be 2 to 1,000 hosts or 2,000 hosts. And what type of automation do I have to manage at that scale? Right? Because I don't have a single application. Now I have 10 or more probably containers. And so there are different ways of doing this: recreate, rolling updates, Bluegreen, and then Canary with ABE testing. So let me walk through these examples. Within Kubernetes, so recreate. This is a very simple way that I just want to upgrade to the next version across my environment in a very simple and automated way. So I have version 1 out in my cluster. There's a security issue. I release 1.2, put it through testing, and what I do is I just bring down that existing version. And then I redeploy with version 1.2. Right? I didn't have to interact the developers. I didn't have to make sure there's backwards compatibility, etc. The disadvantage here is that there was downtime for however long it took me to bring down the cluster and then bring up the new version. That's not good for everyone. So rolling updates is another way to do this, but have zero downtime. Now here I have version 1 out there, and I'm going to do a rolling update with a max surge of 1, so I don't reduce the amount of load I can handle during this process. And I'm going to go ahead and trigger the rollout. And so here you can see it augmented with an additional version 1.2 here, pod. It performed a built-in health check. I could define that TCP, HTTP, or some sort of script. And until that completes successfully, it won't add it in to the rotation. So the service up there was updated once it passed the health check, and then it takes down the old one, so incrementally makes progression towards 100%. You can stop it along the way if you detect an issue and reverse course. Or I go through completion here. And so that was a nice way to have zero downtime, to gradually roll it out so I can control new traffic going on to that new version, kind of monitor, see what the reaction, whether it improves or degrades. And then, one of the cons though is that you have to have backward compatibility, because at previous point in time, I was serving traffic for both version 1 and 1.2. So you need to make sure your database can handle that. So you want to make sure the schema handles both new and old versions. Another choice is a Bluegreen deployment. In Kubernetes, you can do this by creating logical environments. Same physical infrastructure. So I have a logical blue environment, version 1. I'm routing all the traffic through the ingress router. And then I have a new functionality in version 2 I want to roll out. Well, instead of modifying my existing blue cluster, I'm actually going to set up a green environment and call that version 2. Now once it passes its health check, I can switch the traffic to the green. And the nice thing about this, it also didn't have any downtime, and I could reliably go and roll it back to the environment as is. I didn't have to worry about, oh, I made a change and now I have to undo that change, because I never touched the blue environment, right? And so this is probably the most common way to do deployments. The disadvantage also is it takes a little bit more resources because I have I have two environments at the same time. They may have some additional resource needs, and I didn't scale down version 1 perhaps. So That, and then also from a data synchronization, right? You could do replicate the data if you have two different instances. You could also, make sure that you have some backwards compatibility as well with the database if it's a single data store. So next we have ABE testing. So, with microservices, only a third of the ideas improve the metrics they were designed to improve. So we need to foster experimentation, try things out, and enable our developers to do that. And so here we have on the left version A, and in version B we changed the recommendation engine to provide some enhanced, better optimized recommendations. Let's see how it does. And so I'm going to use Canary deployment model. I can deploy version A, and my monitor, the conversion rate's 25%. And then I have this new algorithm. I want to roll it out to some of the traffic. And so I can direct 25% of the traffic to version B, and I can monitor the conversion rate with my monitoring tools. And I saw that it actually click-through rate was 30%. So it's improved, and I'm going to go full into that version. So here I've enabled my developers to confidently test out new versions and give them the ability to try it out to a small sample of my user base. And if there was an issue, I could certainly just revert back to version A. Right? So one of the keys, of course, is to have that continuous feedback loop. So monitoring, logging, giving visibility to my developers, and certain Kubernetes can expose that. Prometheus, we'll talk about on the next slide here, is one of the monitoring solutions, right, to get that feedback loop. So, we're used to monitoring at host level, CPU, memory, etc. Some of the new things in a container world is you need to monitor at the container level, and then also the Kubernetes level from a cluster management perspective, right? And then with the movement from monolithic to microservices, which are distributed across this cluster, you want to have some tools to monitor distributed applications, right? So here's a list of some of the popular kind of open source solutions that are Kubernetes friendly in terms of monitoring at these different levels. Right? So it's important to have a nice tool set when it comes to debugging and et cetera, and getting that continuous feedback loop to you. So what about external services? Right? We've deployed the application, the web server, but my database lives in an external service I need to communicate with. Maybe it's a cloud service. And so here I have a development instance of that service and a production instance. Different IP address for those services. How do I interact with that in a Kubernetes application? So I'm going to go ahead and deploy my web app out to the cluster in a declarative way. And I wanted to switch between these two different external services. And so what I do is I set up a database service, right? This is a cluster IP type, and I named it Mongo, right? So in my application, I use Mongo, right? I'm not hard coding the IP address. Remember, they're immutable. We don't put that in the container image. And so I want to connect to the 10.20.02. And so in order to do that, I define the Kubernetes endpoint. Right? This is just a network IP address and port mapped to the name. And so I change this, the endpoint, to point to the proper database service, rather than changing it in the container. Now, why do you do that? Right? Well, one of the advantages is I don't have that configuration data in the container instance, because if it was and I wanted to change it, I would have to bring down that container instance and restart it, potentially if it was an environment variable, right? And so this allows me to just change the IP address here, and then that service will now point over to the red database. And then, boom, I change it to 9, and it'll change to the blue database. Now, some of these cloud services, they'll give you a dynamic URI with a different port. And so, in order to access that within your application, maybe you have your database user and password specified as a config map or a secret, and then you could access it via Mongo and then specify the port, which would be a config map potentially. In this case, I want the development one. Again, I create a database service, but instead of a cluster IP, I define it as an external name, and it just does a CNAME mapping. So here you have the Mongo 52101.domain.name. I don't put that in the container instance. Instead, I just use Mongo, and it's the mapping for you automatically. Okay. Now, what about databases? Right, we talked about external, but I want to run the database actually in the cluster. Well, first thing you need to be aware of is the context of where the data is being stored and the longevity of that data in the container environment. So first off, you have data in the container. That's actually in the container instance. Well, when I terminate that container, I lose the data. Now, data in a host volume on the local host or the container, the cloud instance that I'm running on, right? The data is lost on the cloud instance when I terminate that instance, right? And then thirdly, the network volume, right? That's independent of the container and cloud instance. So Kubernetes can provision network storage for you in an automated way. So you can pre-allocate and then consume it based on your quota in an automated manner. And so typically that's what I'm going to do. But with a database, there's some idiosyncrasies I want to make sure that I manage properly in this Kubernetes cluster, right? One thing is I want to be able to maintain a sticky network ID across restarts. So that, for example, my MongoDB, I have Mongo 0, 1, and 2, right? Those instances need to be named statically because they need to communicate with each other so they can reroute traffic. For example, maybe only one of those instances has writability, and if I receive write request on a read-only node, I need to redirect it. Also, ordered operations, right? I want to be able to start up 0, then 1, and then 2 in a very specific order. And then when I shut down, I turn off 2, 1, and then 0. I also want to be able to link to that very specific persistent storage for that instance. And I need to have a headless service, not a single IP, because my client is going to communicate directly to the pods. And so with what's called a stateful set, I can deploy that and define that in Kubernetes. So here I define my application to be stateful set instead of the replica set. And I define the replicas to be 2 and my role to be Mongo. So anybody with a role of Mongo is going to be added to that service. And so what initially deployed the first instance, Mongo 0, and it mounted its storage. Now that first one is read-write, and then the second instance, Mongo 1, and then it's to create the third instance, Mongo 2, because I set the replicas to 3. And so here you have the persistent volume claim to the shared storage, the persistent volume. So they're sharing the storage. You have 3 instances of Mongo, and I'm able to access it through the client using the Mongo 0, Mongo 1, Mongo 2, and it will do redirection if it's a write request to Mongo 0. Right. Well, what if one of my nodes is unresponsive? So Mongo 2 is down. I need to replace that. And so Kubernetes will detect that automatically and schedule a replacement node and maintain the name, right? It doesn't become Mongo-3 or 7. It stays to Mongo 2, so it also gets tied to its proper persistent volume claim as well. So the storage went with it. Database migrations, right? We showed you how you can update a typical web service, but how do I deploy databases and then manage updates to the schema in a CICD pipeline on a Kubernetes cluster? Right, so here we go, CICD pipeline. I want to version control the database updates. We're going to use an open source tool called Flyway, of course, to do that. And what I have in production is version 1. In test, I have version 2 of the database. And development, I have version 3, right? So mirrored with my application version number. And I've written scripts to do the schema changes for those versions. And I'm going to leverage Flyway to kind of manage that for me. And so what I want to do in this container world is I have that Flyway version 2 script. I'm source code controlling it, I have a version on it. And then I create a container image from a Docker file, which basically is a Flyway image. And in this case, I'm going to go ahead and put the SQL changes in the file. So here you can see my container image consists of the Flyway, all its dependencies, and then the schema change script. And then I version controlled that image, so I call it version 2. So I have a container image with Flyway and the changes I want to make to the schema in version 2. And so here's my database, currently on version 1. I want to upgrade it to version 2. And what I can do is I can create what's called a job in Kubernetes, so it runs a single time. And I could, in the secret for that job, specify the username and password to do the JDBC connection to the Postgres database. And it will launch a Flyway instance from that image I just created and pull the version 2 from the registry. And then it's going to run Flyway and apply the changes to the Postgres schema, version control that schema as well. And it had that connection info from the secret. Right? And now that database has been upgraded to version 2. Right? So what is one thing that we learned today? Probably want to do it a little differently than I showed you today. Right? You probably want to leverage a config map or a secret, probably a config map for the SQL change. So you don't have to save it in the image necessarily. Right? Optional. So what's next? Talked a lot about managing the microservices and databases, but where is microservice and database management going? Well, next is layering on top with a service mesh. Istio is an example of a service mesh, but really dedicated infrastructure layer. So for service-to-service communication, right? Today, developers are doing that themselves within the container or in the application, and this really takes traffic control, resiliency, chaos, observability, security, extracts that out, and it's also polyglot support. So it's not just language specific like Java. And what does that mean? I thought Kubernetes already had traffic control. We just went through that, right? But that does it on a per pod basis. Traffic control with the service mesh allows you to do it on a percentage basis. Right? So I could route 1% of my traffic. So I could do all sorts of fancy traffic control. I can also do service resilience. That means if a service is not responding, time out, maybe try again in a couple of minutes. Don't bring down the whole infrastructure just because one service is not behaving well. So that's another one. And set the amount of retries you want to do. Also, chaos testing. So if I want to experiment, try things out, see if there's inject some fault, service doesn't respond, how will my application behave to that? So the service mesh allows you to do things like that. It also allows you to do like dark shadow or network traffic mirroring. So you can mirror your production traffic into your test environment and try out your new application on that production that production traffic. And then observability. So using something like a distributed trace tool like Jaeger from Uber, the ability to see your traffic going from service to service, see where the bottlenecks are, etc. And then security. It'll manage service to service mutual TLS for you. It will issue the certs, rotate the certs for you as well. So provide nice security. And then also the architecture, basically what it's doing is it's launching a additional container in the pod, which has a network proxy called, in this case, Envoy. So it's routing all the traffic through the proxy, and the proxy by default blocks all egress traffic. So you don't have to worry about that from a security perspective. You have to explicitly state, right? And it allows you really to manage in a much more automated way at the infrastructure level, service-to-service communication. And then, secondly, what's next? How do you manage in an automated way your services? How do you take that run book and create an automated run book? Well, operators allow you to do that. It's from CoreOS, and an operator really allows you to kind of scale your operations of these services. So think if I'm using an Amazon or a Google cloud service, it does everything for me. Installs, upgrades, high availability, backups. I don't have to worry about that. But what about my ISV app from Mongo or my own internally developed app? I want to have that same automated quality of service that I get with a cloud app. Well, the operator provides the framework to enable that automation for you in a Kubernetes native manner. Basically, it's creating a resource type within Kubernetes and a controller that monitors and manages that for you. So, for example, it could monitor my cluster and detect if the cluster is at version 1 and for some reason one node got to 1.1, one of the pods was upgraded to 1.1, it could automatically detect that and bring back the cluster to 1.0 for me. Right? I wouldn't have to manually detect that and fix it. It would do that automatically for my custom app. And then thirdly, Knative. This is about bringing serverless in a standardized way across any provider to Kubernetes. So an active project here. One thing is it allows you to kind of build pipelines for your functions, also enable you to have an event-driven kind of Lambda-like experience, serverless experience on top of Kubernetes in a Kubernetes native way. And then, of course, source events and then trigger actions based on those to launch those functions for you. And so that's an area of active development on top of Kubernetes from the Kubernetes community. Right, so service mesh, operators, and Knative, certainly some big innovation going on around the Kubernetes space in 2019. So with that, I want to thank you very much for attending today's session. I'm going to be around outside if you have any questions. Here's my email and Twitter as well. Thank you so much.